Welcome. Let's take a look at number 3. Of the people who fished at Clearwater Park today, 42 had a license and 28 did not. Of the people who fished at Mountain View Park today, 42 had a license and 18 did not. No one fished at both parks. Suppose that one fisher from each park is chosen at random. What is the probability that the fisher chosen from Clearwater had a license and the person chosen from Mountain View did not have a license? All right, so let's start with organizing the information here. So just to abbreviate, I'm going to just call Clearwater CW. Clearwater Park, I had 42 people with a license plus 28 without a license, giving me a total of 70 people fishing there. And then at Mountain View Park, I'll just call it MV here for Mountain View, we had 42 people with a license plus 18 without a license, giving us a total of 60 people fishing there. Okay, so we have independent events because the person I pick from Clearwater doesn't affect what person is chosen from Mountain View Park. And in particular, we'll be looking for the probability that, I'll do a little abbreviating again. So the probability the Clearwater person picked had a license. So I'll just write Clearwater L for license. So Clearwater Park had a license and the person from Mountain View Park did not have a license. So I'll use my complement notation, L for license, and a bar over it is not a license. So just so I can have some notation going on here. And then we're ready for the multiplication rule. So I'm just going to come over here and circle. So Clearwater with a license was 42 out of 70. So that's the chances of getting a Clearwater Park with a license. And then we'll multiply that by, we want the Mountain View Park person to not have a license. That was 18 people out of 60. And they say to express the answer in decimal, so there's many ways you could enter this. I'm going to just enter it on the calculator the way I speak it. So I'm just going to type 42 divided by 70 times 18 divided by 60, and that is 0.15. So they ask for decimal, so that is our answer, but I'm going to just speak it here as a percent. So there's a 15% chance that those events occur. All right, number 4. A student randomly guessed the answers to 3 questions on a multiple choice quiz. Each question had 5 answer choices, A, B, C, D, E, one of which was correct. Find the probability the student guessed correctly on the first 2 questions and then incorrectly on the third question. All right, so let me write that question in symbols here. So we want the probability that, I'll just do C for correct. So they got the first one correct, and they got the second one correct, and then they got the third one incorrect. So I'll just use an I to write our abbreviation there for incorrect. So there's our first question, our second question, and our third question. So we'll go one question at a time and multiply. So if this is a question with 5 choices, the chance of guessing correctly, 1 out of those 5 is correct. So we have a 1 in 5 chance of guessing a question correctly. And then if we're randomly guessing on the next question, so again, a 1 in 5 chance of getting it correct. And then an incorrect guess, if one is correct, the other 4 of them are incorrect answers. So always a 4 in 5 chance there of guessing incorrectly. And then we're going to write the answer as a fraction and a decimal. So let's do fraction form. Multiply the numerators, that's 4. And if you multiply the denominators, 5 times 5 times 5 is 125. So there's your fraction answer. And then I will also go ahead and write that in decimal form, which is 0.032. And again, just to speak it here, there's a 3.2% chance of guessing correct, and then incorrect on the third question. All right, one more example of independent events. So a spinner has 10 equally sized regions. One is red, 9 of the regions are green. We're going to spin the spinner, and at the same time, we're going to toss a fair coin. So of course, what happens on the spinner has no influence of what happens on the coin. That's why these events are independent of one another. What is the probability the spinner lands on green and the coin toss lands head? So we want probability of green. We'll just do the G there, green on the spinner. And I'm sorry, it says tails. I think I said heads earlier, but the coin toss lands tails. So green and tails. All right, so we just do one at a time here. We'll start with getting green on the spinner. So 9 regions out of the 10 are green. So a 9 in 10 chance there, times the probability of coin toss lands tail. So the coin has 2 sides. One is a tail. So 1 out of 2. And I'm just writing this one again as a fraction. Multiply numerators, multiply denominators. So that would be a fraction answer. And then I'll go ahead and write that as a decimal. So 0.45. And then finally, to speak it, 45% chance. Spinner lands green and the coin lands tails. All right, so we're ready to move forward into cases where events are not independent. So we're going to look at dependent events and see how this affects the multiplication rule. So there's some new symbols to learn here, which we'll get to in a second, but let me set this up with our example. So it says sampling without replacement. This is going to cause dependent events. So in other words, what happens on one event will influence future probabilities on events. So let's take a look here. A bag contains 2 blue marbles and 4 red marbles. So I have my bag here, 2 blue and 4 red. We're going to remove a marble from the bag and record its color. And then we're not going to replace it in that bag. So we call this sampling without replacement. So we take it out, record the color, and we hang on to it. We don't put it back. And then we're going to remove another marble from the bag and record its color. So let me start with this first example. So I'd like to find the probability the first marble is blue and the second marble chosen is blue as well. So I'm going to do a little bit of organizing over here. So the idea is we start with blue, blue, 2 blue, and 4 red, 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 red. So those are the marbles in the bag. And what I'm going to be doing is picking a marble and trying to find the probability it's blue. So the first round of picking, I have 2 blue and 4 red for a total of 6 marbles. And I want to know the probability of picking a blue one. So 2 out of the 6 are blue. So that's our first round. So the idea is we assume then that we've taken out that blue marble and we're not putting it back. So at this point, I'm going to cross out one of those blue marbles. So I'm going to pick a blue marble, but I don't replace it. So this is the sampling without replacement. So in the bag there, that blue marble is basically now no longer present. So let me see what I have if I'm ready to pick another marble. So if I pick a blue marble, I'm going to cross out 2. There's not 2 anymore. There's only one blue left. There's still 4. We didn't take out any red. And in total, 1 plus 4, that would be 5 remaining marbles. And then we're going to find the probability the second one is blue. So in my second round of picking, I've got 1 blue marble in the bag. There it is, 1 blue, and 5 marbles that I'm choosing from. So this is my probability of a blue and then another blue. So let's see what the notation looks like now. So when I picked up that blue marble and didn't put it back, all future probabilities would change because we would no longer have the 6 marbles. All right, so we have dependent events. What happens on the first event affects future events. So let me show you notation. So it's still the multiplication rule. It's still the multiplication rule. So we would find the probability, the first one is blue. I'm just going to write probability of blue. And then we're going to multiply that by the probability that the next one is blue. But knowing that we already took out the blue one. So it's the probability of blue times the probability the next one is blue. And then we say given that or knowing that, and it's just a little vertical line there on a keyboard. It's called a pipe, little vertical line, and it's read given. So we want to know the probability the second one is blue, given that the first one was blue. So I know it looks a little bit strange here, but we'll just talk it through again with numerical values. So we would say, what is the probability of getting a blue marble? 2 out of 6 times. Now, what is the probability of getting another blue one, given that that first one was blue? So that's what the table sets up for you. So knowing I took out a blue one, the probability the next one is blue, 1 out of 5. And then I'm just going to multiply and leave this as a fraction. So 2 out of 30. We don't need to reduce or anything here. So let's just get the concept. So let's try this again. So what if I wanted to know the probability of getting a blue marble followed by a red marble the second time? All right, so the notation would be, I want to know the probability of getting a blue. So I would take probability of blue times, and then now I want the probability that I get a red marble, given that, knowing that you just took out that blue one. Okay, and I'll use the table again just to organize us a bit. So I'm going to start with 2 blue, 4 red with 6 marbles. So the chance the first one is blue would be 2 out of 6. So let me just write that first here. So that would be 2 out of 6 times. So on my next round, we already took out a blue one. So I'm going to cross out the 2. We'd be down to 1 blue, 4 red, 5 marbles. And now I want the second marble to be red. So still left in the bag, we would still have 4 red, and it would be 4 out of 5. So I'm going to do this at the top one more time just to make sure you've got it. So we had 2 blue and 4 red. The first pick, we took out a blue. I'm going to cross it out. We took out a blue. So we would still have the 4 red, the 1 blue, and that's the 5. So red would be 4 out of 5. And then we just multiply. Okay. So let's try the next one here. All right, now it's what is the probability of red on the first marble and blue on the second? So now we would say it's the probability of a red and then multiply, and then the probability the next one is blue, given that, knowing that you've already removed that red one. So I'll step through with the table again. So we have 2, 4, 6. And now we're starting with the probability of getting a red. So that's 4 out of 6. So I'm going to write that 4 out of 6. And then we say, basically, you just pretend that just happened. You just picked up a red marble. You're hanging on to it. You don't put it back. So when I'm ready for my second round of picking, there's still 2 blue, but I took out a red one. So there's no longer 4 of them. We'd be down to 3 of them. And then no longer 6 marbles, we're down to 5. And actually, if you want to kind of be consistent with my crossing out, so 6 goes down to just 5 marbles. And then I want the next one to be blue. So 2 out of those 5 are blue. So I'll do a few problems where I keep making a table for you, and then you can choose to use it or not. If it helps you be organized, great. Or if you can just visualize it, that's fine as well. So last one here, the probability that a red is first and then another red. So this would be probability of a red times the probability the second one is red, given that we just took out that first one that was red. All right, so I'm just going to note here then that that vertical line is red given that. You can think of it as knowing that something just happened. So the beginning point 2, 4, 6. Probability of a red, 4. 4 out of those 6 are red. And then the probability the next one is red, but you know that you took out the red the first time. So on my second round, I still have 2 blue, but I'd be down to 3 red. I'd be down to 5 marbles. So the probability of getting another red one on the second pick, there'd be just 3 red left out of the 5. All right, that will be 12 out of 30. All right, so the reason I didn't reduce the fractions, I'm just going to box these in, is because I just did every possibility of recording colors when you pick 2 marbles. So if I were to add up all these probabilities, the denominator is 30, so we have a common denominator. And if you add the numerators, you'll get 30. So 30 out of 30, or 1. So there's a 1 or 100% chance that you would get one of these sequences of colors anytime you take 2 marbles out of that bag. All right, more examples to come.